So we're going to continue with Chapter 15, talking about buffering capacity. Okay, so the amount of protons or hydroxide ions that a buffer can absorb without a significant change in pH is called its buffering capacity. Remember, a buffer is something that doesn't have a big change in its pH. And so we're going to look at different types of buffers and, how much H plus or OH minus a buffer can absorb without a change. So the pH of a buffered solution is determined by the ratio of the conjugate base divided by the concentration of the weak acid. And so we can determine the capacity of a buffered solution by looking at the magnitudes or the amounts of the concentrations of the weak acid and the conjugate base. So let's look at an example. Okay, so we want to calculate the change in pH that occurs when 0.01 moles of gaseous HCl is added to 1 liter of each of the following solutions. So we've got two different solutions with very different concentrations that we're going to look at. And we also have the Ka value. Okay, so we know that we can use the Henderson-Hasselbalch equation to calculate the pH. Because this is a buffer, we're going to assume that the initial concentrations are equal to the equilibrium concentrations. And since we want change in pH, we know that change in pH is equal to the final pH minus the initial pH. And so first, let's look at calculating initial pH for solution A. Okay, so we know that the Henderson-Hasselbalch equation is pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. So for A, pH is equal to negative log of 1.8 times 10 to the negative fifth plus log of the conjugate base. They're both for solution A 5 molar, so that's 5 molar on top, divided by concentration of the acid, which is also 5 molar. So 5 divided by 5 gives us 1, so that's natural log of 1, and so when we do that math, we get 4.74 for our pH. Now, the pH initial for solution B is actually also going to be 4.74, because even though the concentrations are different, the ratio would be the same. 0.5 over 0.5 is also equal to 1, and so our math is going to come out the same. So for both solutions, we have an initial pH of 4.74. Now let's calculate final pHs. Okay, well, let's look at pH final for solution A. Okay, we know that the major species are going to be our acetic acid, so HC2H3O2. We also have our salts, so Na+, C2H3O2-, and then because we are adding HCl, and that's a strong acid, we've got H+, Cl-, and also water. Well, we know that the H+ isn't going to contribute at all. We know water is a weak acid or a weak base. We know the chloride ion won't combine with H+ in water, so that basically leaves us with these three. So we've got H+ plus C2H3O2 going to our acid, which is C2H3O2. Okay, so now we want to calculate before concentrations and after concentrations. So the H+ initially is coming from our HCl, so that's 0.01 molar. And the concentration of our C2H3O2 is coming from the salt, which was initially, or before the reaction, 5 molar. And then we know that we're starting with 5 molar of our acetic acid. Okay, after we react the HCl, we know that all that H+ is going to go with the acetate ion to form acetic acid. So we're going to have no H+ left. We know this is going to be 5 minus our 0.01, so 4.99. And we know that here, since we're adding the H+, it's 5 plus 0.01, and so we know that that's 5.01 molar. Okay, so now we can again use the Henderson-Hasselbalch equation using our after reaction concentrations. So pH is equal to pKa, which was negative log of our Ka value, which was again 1.8 times 10 to the negative fifth, and then plus the log of our base, which in this case is our 4.99 molar, divided by our acid, which is our 5.01 molar. And if we do some math here, we know that that negative log of the 1.8 times 10 to the negative fifth is the 4.74, and then our log of our ratio is 0.0017, and so really, since this is so tiny, we're just going to get 4.74. So for solution A, our change in pH is really 0 because our final is 4.74, our initial was 4.74, and so we're getting 0. So this says that we have a very large buffering capacity because the addition of HCl is not changing the pH at all. And let's look at pH final for solution B. So we have our same reaction, same major species. Okay, so we've got different starting concentrations. Our HCl is still the 0.01, although now for our acetate ion and our acetic acid, we're starting with 0.05 molar. So this would be before the reaction, and then after the reaction, no H plus because it's going to completely react. This would be subtracting 0.5 minus 0.01, so that's going to give us 0.04. And then here we've got 0.05 plus 0.01, and so that's going to give us 0.06. And so now we can again use the Henderson-Hasselbalch equation. pH equals pKa, which is 4.74, plus the log of our base, 0.04, divided by our acid, 0.06. And that gives us our 4.74 minus 0.18, which gives us 4.56. So now our change in pH for solution B is our 4.56 minus our initial, which was 4.74, and so that does give us a small change, but still a change. And so we can see that for solution B, its buffering capacity is not as great as that for solution A. So let's talk about optimal buffering. What's the best concentration we can have to get optimal buffering? We know that large changes in our ratio are going to cause large changes in pH. So that would not be a good buffer because we don't want to change in pH. If we have a good buffer, pH shouldn't be changing. So there's two ways that we can change that ratio. We can have a large concentration of HA and a small concentration of the conjugate base, or we can have a large concentration of the conjugate base and a small concentration of the acid. And well, we don't want either of those things. We want optimal buffering. So the best way to have optimal buffering is to have equal concentrations of both the weak acid and the conjugate base. And if those are equal and we put them together in our ratio, that means that our ratio is equal to 1. So the best buffer you can have has a ratio equal to 1. Well, if we take this and use it with our Henderson-Hasselbalch equation, we can see that if we make this ratio equal to 1, that gives us pKa plus log of 1. Well, log of 1 is going to cancel, so we're just going to get that the pH is equal to pKa. So, in general, the pKa of the weak acid used in the buffer should be as close as possible to the desired pH. So, we want our ratio to be 1, and then we want our pKa really close to our desired pH value. Well, let's look at another example. Okay, so a chemist needs a solution buffered at a pH of 4.30, and we've got 4 acids to choose from. So we want to calculate the ratio required for each system to yield a pH of 4.3. We want to know which system is going to work best. Okay, well, there's 2 ways we can go about this. We could use the Henderson-Hasselbalch equation and find one where the pKa is equal to that pH of 4.30. So we could go through and do negative log of all these. But since we have Ka values and not pKa values, let's find that ratio instead using the rearrangement of the equilibrium constant, and then we can look for a ratio close to 1. So there's two different ways you could do that. So let's start with finding what we want our H plus concentration to be. Well, we know that our pH is 4.30. That's what we're trying to go for. So this means that our H plus concentration is equal to 10 to the negative 4.30. Well, if you do that math, you get that 10 to the negative 4.30 is 5 times 10 to the negative 5 molar. So that's the concentration we want for our H plus. We know that H plus is equal to the Ka value times the concentration of the weak acid divided by the concentration of the conjugate base. And this just comes from the rearrangement of the equilibrium expression. Ka equals H plus A minus over HA. Okay, so that's where that's coming from. Okay, so if we rearrange this to solve for just our ratio part, then that means that H plus over Ka is equal to our ratio, acid over conjugate base. Alright, so let's look at acid mixture A. So we know that all the Ka's, it was given that the Ka, alright, so we got Ka for each of these, and then we have our H plus. Okay, so our H plus is 5 times 10 to the negative 5th, and solution A, the Ka value is 1.35 times 10 to the negative 3rd, and so if we divide those, we get 0.037. Not very close to 1, so A is probably not going to be the solution we want. Okay, let's try B. 9.0 times 10 to the negative 5th, because we're following this same equation for everything. Ka for B is 1.3 times 10 to the negative 5th. We divide those, we get 3.8. Still not very close to 1. Let's go to C. Okay, plug into the same equation, 5 times 10 to the negative 5th molar. Ka value for C is 6.4 times 10 to the negative 5th. Divide those, we get 0.78. Alright, that one's kind of promising, close to 1. Let's try D. Same equation, 5 times 10 to the negative 5th. Ka value for solution D is 3.5 times 10 to the negative 8. And that is 1.4 times 10 to the 3rd. Ooh, gigantic number. Not even close to 1 at all. So it looks like our winner is solution C because it has the ratio closest to 1. Okay, so this is where we got all of our Ka values. They were given to us. Okay, so solution C was benzoic acid. So that means that benzoic acid is the best solution to use. Okay, so here are some problems to work on, and we'll discuss this more in class. Have a good day.